So the last section we're going to take a look at is 6.5, and it's on solving right triangles. Okay? Basically finding trig functions of acute angles. If you know a little bit about right triangles, you know that the angles in a right triangle are always acute. They have to be, because all the angles add up to 180. And if you already got a 90, the other two have to be smaller than 90. Okay, so just a couple kind of basic reminders about right triangles and some different terms we'll use. Okay, so right triangle means that you have a 90-degree angle. What's the side across from the 90 called? Hypotenuse. And what are the other two sides called? The legs. Okay, so hypotenuse always across from the 90. Legs are the other two sides. Okay, so here's a picture of what we just said. Usually, when we label sides in a triangle, we use English letters, like ABC. When we label angles in a triangle, we use Greek letters. Okay? That just makes it clear what we're talking about. I think in our book, they use lowercase letters for sides and capital letters for angles. I don't really like using lowercase and capital, because then if you ask me, like, how did you get B? It's confusing, like which one, capital B or small b? So there's a difference. And then some letters, capital and lowercase, look the same, like C. So when you write C down, it's hard to tell if you mean capital or lowercase. So we're going to stick with Greek letters for angles. Then there won't be that confusion. So both angles that are not the right angle have to be acute, or the triangle wouldn't add up to 180 degrees. Now, you've probably always been told that the angles in a triangle have to add up to 180. And for a triangle like a flat triangle, they do in the plane. But if you start to talk about triangles, there's what we call a spherical triangle. And you could imagine, like, if you connect the North Pole, Boston, London, that's a triangle. But it's not a triangle like you draw on a flat surface, because Earth isn't flat, it's curved. That kind of triangle is different. Okay, that gets into what we call spherical geometry. So we stick mostly with Cartesian, right, which means flat. Okay. All right, so there's a theorem that we can use that involves all the sides in a triangle, okay, and that is the Pythagorean Theorem. Okay. Usually that's how you write it, but the idea is that if you take a leg and square it, plus another leg and square it, it's equal to the hypotenuse squared. Whether you call the sides ABC, D, E, F, doesn't really matter, but ABC is the most common. Now, I'll look at that diagram. Has anybody ever seen a proof of the Pythagorean theorem? Okay, so maybe you can help me because I don't remember how to do it. So we're going to look at this, and we're going to do something. We are going to find some areas. Okay? Right. We're going to find some areas. What we're going to do is I want to find the area, I think, of the big square. Two different ways. By big square, I mean this. I want to find the area of that big square. What's the formula for the area of a square? S squared, or length times width. Length and width are the same. So what's the length of one of the sides? A plus B. Okay. So let's write it like this. Area of a square equals, I'll just say length times width, or side squared, same thing. Well, the length is A plus B. So let's outline this in black. Let's call this the black square. So area of black square. A plus B. That's the length. What's the width?
A plus B.
It's also A plus B. Now let's FOIL that out, simplify it, and what would you get?
A squared plus BA plus B squared.
A squared plus
BA.
2BA, or 2AB, same thing, plus B squared. Okay. Anyone disagree that that's the area of the square? Black square. Okay, now we're going to find the area of a black square a different way. Instead of thinking of it as one big shape, we're going to break it down into smaller shapes. Anyone think they could give me like kind of the idea behind that way to do it? Find the area a different way by adding up other areas?
Like adding up the 4 triangles and the square inside the larger square.
Because that should be the same thing. Adding up the area of those 4 triangles plus the area of that square that's on a kind of rotated a little bit should give me, it's the exact same thing. Just adding up the pieces rather than looking at it as the whole thing. Okay, so let's call this box 1. Now we're going to find the area of black square again. A little bit different. Let's start with the area of the square inside. What's that?
C squared.
C squared. C times C. Plus. Now, how many triangles do you have inside?
4.
4. And how do they all compare to each other? They're all the same. They're all congruent. The reason they're all congruent, you can go back to geometry, but they have a side, 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 and I think the easiest way would just be to say side. Side, side, side. Okay? But there's all kinds of ways to prove all 4 of those triangles are congruent. All right, so we got that. What's the formula for area of a triangle? 1/2 base times height. So all I have to do is find the area of one of those triangles and do what with it? Multiply by 4. So 4 times 1/2 base times height. Okay, let's look at, it doesn't matter how you really view it, but let's look at this one. What's the base there? And what's the height? A. All right. So B, A, or AB, doesn't matter. Questions on that? Let's simplify it. It's going to end up being C squared plus what? 2BA or 2AB, same thing. And we'll call that box 2. Now, box 1 is a way to find the area of the black square, so is box 2. What does that mean about the expression in box 1 and the expression in box 2? They're equal. So now, write that down, and then you'll have the Pythagorean Theorem. So, a squared plus 2ab plus b squared equals c squared plus 2ab. And what can I do on both sides? Subtract the 2ab. Gone? Gone? So there is the Pythagorean Theorem. A squared plus b squared equals c squared. So very, very easy to prove. It's one of those formulas, you can really prove it. I think there's probably 50 different ways to prove that. Most of the ways I know involve drawing a diagram and finding areas. But there's tons and tons of ways. At least this one you can pretty much do with nothing more than algebra 1 and a little geometry.
Is there going to be a question like this one on the test?
How to prove the Pythagorean Theorem?
Yeah.
No, I've already done it. No, I'm not going to ask you how to prove something I've already done, but it could tie into something else. We are going to use the Pythagorean Theorem a lot. But any questions on how we proved it? All right. So let's take a look at a couple other things. So we've gone through the 6 trig functions before. And we did them on the unit circle. where we had like sine was y, cosine was x, tangent was y over x. Okay? That's fine, okay? But that's using what we call unit circle trig. Now we're going to look at how to do it in terms of a triangle. And then I'll show you the connection between the two. Okay, the way I taught you before and what I'm showing you right now, same thing. Just giving stuff different names, that's all. So, first three trig functions are sine, cosine, tangent. And the definition of sine, it's a ratio of the length of two sides, two specific sides. The length of the opposite side over the length of the hypotenuse. Cosine is also a ratio of two sides. It's the length of the adjacent over the length of the hypotenuse. And tangent, our last one, is a ratio of the length of the opposite to the length of the adjacent. So, what does that mean if you divide two lengths? Think about what your units would be. Like 8 feet divided by 10 feet. Would be the unit. Which one? Degrees or nothing?
It'd probably be degrees.
So if you divide feet by feet, it turns into degrees. It cancels, right? If you've got 3 feet divided by 4 feet, feet cancels, and you're left with just a pure number with no label. So anytime that you find a trig function, right, use the calculator or do it by hand, there is no label on your answer. If we're doing inverse trig, that's different. This is just regular trig. The inverse has the little -1 up here. Some of you have seen that or asked about it on the calculator. That's different. But trig functions, it's just a length divided by a length. It's just a pure number. There is no label. Yep.
So if there's like no label, like what is it for? You know what I mean? Like what does it mean?
You'll see what it's for in the next part. It's basically used to find out how long a side is or how big an angle is in a triangle when you don't have all the information. All right. Now, the other three are your cosecant, your secant, and your cotangent. And what was the connection between sine and cosecant? They are what?
Inverse.
Not inverse. Reciprocal. Yeah, flip. So what do you think the cosecant is?
Hypotenuse over opposite.
Yeah, hypotenuse over opposite. The secant is adjacent over hypotenuse over adjacent. And the cotangent is adjacent over opposite. Now, remember, I don't know if I've said this to you or not yet, but opposite and adjacent are what we call relative terms. They're relative to an angle in the triangle. It's like if I said to you left and right. Well, you couldn't put like a sign on this wall, say in the room here, saying which way is left. Because left depends on which way you're facing. If you're facing the door, left is the board and right is the back wall. If you're facing the back wall, then left is the door and right is the windows. So left and right depend on which way you're facing. That's kind of how opposite and adjacent are. They depend on which way you're facing. Okay, and I think in a second, I'm going to mention that. Actually, you know what? Maybe I'll mention it right now. So if you have a triangle, and they put theta there, that is your reference point. That's like where you're standing. So opposite and adjacent are from the perspective of this spot. Opposite means furthest away. It's basically the side that if you got rid of it, it has nothing to do with that angle at all. That angle is still right there. You didn't mess that angle up. Adjacent is the side that's right next to the angle that's not the hypotenuse. If you get rid of the adjacent side, you don't have an angle there anymore. You just You just got rid of one of the sides of the angle. So that angle is now gone. Okay? So opposite is the side that's furthest away. Adjacent is right next to it. And that's the hypotenuse. Now, you could take same problem and switch the perspective of how you're using the trig functions. If the perspective is from the angle down here, where is opposite now? Yeah, the opposite is now, it's like your height. That's opposite. That's adjacent. Okay. Any questions on those two words? All right, now, I said to you this is exactly the same as what we did with unit circle trig. I think I said it earlier, but does anybody remember when we did unit circle trig, sine was what letter? Sine was y. Yep, cosine, x, and tangent, y over x. Well, draw a diagram, make a triangle, call this side x, this side y, and that side your hypotenuse, which actually in a unit circle is how long? 1. Okay. Let's use the definitions I just explained and see what happens. Sine is opposite over hypotenuse. Looking at my diagram, what side is opposite theta? Y over, what's the hypotenuse? 1. And y divided by 1 is y. Cosine is adjacent over hypotenuse. X over the hypotenuse is 1, and that's how you get x. Tangent, opposite over adjacent. Y over x. So all the definitions we did from unit circle trig really just are these definitions. Same thing. And the last thing about these, there is a way to try to remember them. Anybody know the trick? Yeah, Sakatella. So, sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. Okay. And if you spell it out, it's Sakatella. One year I asked how we can remember it, and somebody said Sacagawea. She's not going to help, but Sakatella will help you more. So just keep that in mind. The other three, there really isn't a good way to remember it, like using the letters. It doesn't really spell anything nice. But if you just remember, flip what's on the left to get what's on the right, then you're good. Okay. If you have two right triangles with all the angles the same, that means your triangles are similar. So what that means is that if you're dealing with two triangles that are similar, you will always get the same value for a trig function. Like if you draw a big 30-degree angle or a smaller 30-degree angle, it doesn't matter. It doesn't matter. The answer when you do trig with a 30-degree angle is always the same. So here's an example. The one on the left is a smaller 30-degree angle. The one on the right is bigger. It's part of a bigger triangle. Does anybody see what the scale factor is between the two? 2. One on the right is double the one on the left. So let's find the sine of 30 for the triangle on the left. Sine is what over what? And what's opposite 30? 1. And what's the hypotenuse? 2. So the sine of 30 degrees in that specific triangle is 1/2. Now, let's find the sine of 30 degrees in a bigger triangle. What's the side opposite 30? 2. What's the hypotenuse? 4. What's 2 over 4 reduced to? 1/2. Okay. So the point is, the size of the triangle does not matter at all. Okay? The sine of 30 degrees is always 1/2, whether you draw a really small triangle or you draw a really big triangle. Okay? So what that means is when we have to figure out trig functions, especially multiples of 30 and 45, okay? Eventually we have to know how to do those in our head. Ones that are not multiples of 30 and 45, no. Usually we'll use a calculator. But 30s and 45s come up a lot, okay? All the time in calculus. So we have to know those. So if I have to figure one of these out in my head and I can't do it, I think of a triangle that I can draw, but I try to draw the smallest one that I can to keep the numbers simple. I don't try to draw a huge one, because then I got bigger numbers. Okay? Smaller numbers will give you exactly the same answer as bigger numbers.
Does this only work on right triangles, or?
What's that? The similarity idea?
Yeah, like the sine, like opposite.
Oh, the opposite adjacent hypotenuse, yeah. Because if you don't have a right triangle, you don't have a hypotenuse. So when we get into triangles that are not right triangles, we have to use either the law of sines or the law of cosines to solve them. Okay, but for this week, opposite adjacent hypotenuse, SOHCAHTOA, that'll work. Okay, so how do you find the 6 trig functions of an angle if I give you one of them? So basically, I'm going to give you a problem like that. We'll come back to this in a second. In that problem, I'm telling you the sine. Can anybody be more specific about what I'm telling you? Yes, the sine is 5/6, but can you give me more detail? The opposite is how long? 5, and the hypotenuse is 6. I have 2 out of 3 sides of the triangle. Well, if you've got 2 out of 3, how can you get the one you're missing? Use the Pythagorean Theorem. Yep, that's basically what that says. So take the 2 sides that you're given, use them to label the 2 sides of a triangle, figure out, do you have opposite, do you have adjacent, or do you have hypotenuse? You'll have 2 out of 3. Use the Pythagorean Theorem to get the side you're missing. Now you've got all the sides, and you can find anything you want. Okay, but that's where the Pythagorean Theorem is going to come in. Now, since you're going to have 2 sides right away, there's 2 functions you can find without any work at all. You can find the one they give you, like sine, and you can find its reciprocal, cosecant, because all you have to do is flip it. But to find the other 4, you're going to have to use Pythagorean Theorem. Right. So, in this case, I mean, if you need to draw it, you can. If you can do it without, that's fine too. Doesn't matter where you put theta. Just now it matters where we put the 5. You guys said the 5 is opposite. 6 is the hypotenuse. Solve for adjacent. All right. What would be my equation to solve for the... And what would it be if we plug in those numbers?
A squared 25 equals 30.
Yep. So a squared plus 25 equals 36. 36 minus 25 gives me 11. And a is the square root of 11. Generally, we leave the answer as a square root unless they say not to. But let's leave it as a square root. So let's write down all 6. What's the sine? Yeah, 5/6. What about the cosine? Square root of 11/6. And tangent. Yeah, it would be 5 over the square root of 11, but once you fix it, 5 square root of 11 over 11. If 5 and 11 reduced on the outside of the root, if it was like 6 over 12, you can reduce that. Okay, cosecant, 6 over 5. Secant,
6 square root of 11 over 11.
Yeah, I'm just going to put it over here. Yeah, and this one, you might say, well, how should I get the tangent? Should I just flip this? No, I would think about it the way it was originally. It was 5 over the square root of 11, so it's the square root of 11 over 5. Cotangent equals square root of 11 over 5. Now, on a problem on the test, I'm not going to ask for all 6 in the same problem. This would be 6 problems on a test. So I'll probably ask you for 2 of them. I might say, what's the cosine and what's the cotangent? In 2 separate problems. Okay. Questions on that? All right. Anybody know what the hypotenuse is right away there? No.
Square root of
13. Does anybody know what that's called? That has a special name. Pythagorean Triple. That's a Pythagorean Triple. So a Pythagorean Triple is just a triangle where all the sides are nice numbers, all integers. 3, 4, 5 is another one. Some people remember the 5, 12, 13. Not a big deal if you don't. 5 squared plus 12 squared is 169. Take the square root and you get 13. So what's nice about this is you don't have to worry about square roots. So no flipping or fixing anything like that. What's my sine? 5 over 12. Cosine? 12 over 13. And my tangent? Yeah, what's my sine again? 5 over 13. Did someone say 5 over 12? No, maybe I just heard wrong. But yeah, 5 over 13, 12 over 13, and tangent is 5 over 12. Okay, 5 over 12. And then you would flip them. 13 fifths, 13 twelfths, 12 fifths. Questions on it? Yeah.
If they do work out the whole numbers, you put the decimal numbers, right?
Yeah, you could. Like if it ended up being like 6 divided by 3 and you could write 2, yeah, that's fine. Most of the time it ends up being fractions. A lot of times it ends up with square roots. Most of the time. Unless you have a Pythagorean triple. Okay. Now, I want to use that diagram to find the 6 trig functions of 45 degrees. Now, let's say I just gave you that. What kind of triangle, if you draw a 45 degree angle in a right triangle, what kind of triangle did you just make? Yep, it's isosceles. So remember what I said. Does it matter what size triangle you make to find the sine of 45 degrees? No, so make the smallest one you can. Right? All you have to do is stick to the definition that this is isosceles, which means these 2 sides are the same. So pick any numbers you want. Just keep them the same. So what numbers would be the easiest? 1, 1, square root of 2. If you said, well, I'm going to make this 4, that's okay. 4 squared plus 4 squared would be 32. And then this would be the square root of 32. That's just a bigger version of a 45, 45, 90. You will get the same answers. Okay. So what is my sine there? Well, I guess maybe I should say pick your perspective, where you want to stand in the triangle. You have to pick the angle that's 45 degrees.
Oh, yes.
So it doesn't matter. Let's pretend like we're standing here.
So square root of 2, 2.
Yeah. It's going to be 1 over the square root of 2, but then you're going to fix it. And what about your cosine?
Same thing.
It's the same thing because the opposite and adjacent are the same thing. So that's also square root of 2 over 2. And what about your tangent?
1.
Yeah, dividing 2 things that are the same, you get 1.
So it's kind of unit circle.
Kind of, but in the unit circle, we would have let the hypotenuse be 1, and we would have had this side be root 2 over 2 and root 2 over 2. I think as long as you put a 1 in the triangle somewhere, it makes it pretty easy to work with. What's your cosecant? Square root of 2. But if you notice, if you compare all these answers to what we did for a 45-degree angle before, these are all the same answers. Because it doesn't matter what size triangle you use. What's your secant? And your cotangent? 1. So there's 6 trig functions of 45 degrees. All right. So, let's say I gave you this problem. And I said to you, find the 6 trig functions of a 30-degree angle. And my hint is to start with that. What kind of triangle is that? It's equilateral. Right? So let's suppose each side is 1, 1, and 1. I don't know if that's the best number to pick, but we can go with that. 1, 1, and 1. How can I get a 30-degree angle somewhere in there? Yeah, split it right down the middle. And that does a couple things for you. If you split it right down the middle, let's look at this triangle. Well, this side is 1. How about the bottom side? Right, you split it right down the middle. That's an equilateral triangle. You can prove that if you draw in the altitude from the vertex to the base, it does bisect your triangle into 2 congruent triangles. So this is now 30, 60, 90. That's 1/2. And how can I get the third side?
1/2 squared plus b.
1/2 squared plus, b squared equals 1 squared. So this is where if you picked a nicer number, like maybe if you let all the sides in this triangle be 2, you would have gotten less fractions, because then you would have had a side of 2 and 1 instead of 1 and 1/2. Okay. So when we square a half, what do you get?
0.25.
0.25. And what's 1 minus that?
0.75.
And we're going to take the square root of 0.75, which is root 3 over 2. These are the exact numbers we used when we did unit circle trig. Imagine your circle just like that. Your radius is 1. That's the center of your circle. So 1, 1/2, root 3 over 2. Any questions on how you would find the 6 trig functions of 30 and 60 from here? You just have to change your perspective. Do the problem once from here, where 1/2 is opposite and root 3 over 2 is adjacent. And then do it again from here, where now root 3 over 2 is opposite and 1/2 is adjacent. Any questions on that? Okay, so the only thing I think you had to be a little clever about here was splitting the triangle down the middle to create a 30-degree angle. It's the only part. Other than that, as long as you pick a somewhat nice number for the sides, an even number would have been better, because when you take half of it, you wouldn't have had a fraction. So 2, 2, and 2 might have been an easier way to go. Any questions on that? All right. So, what does it mean if 2 angles are complementary? They add up to 90, right? And remember, they have to be acute. Now, how come the 2 smaller angles in a right triangle will always be complementary? We've already kind of answered this in different ways.
Because the inside angles of the triangle add up to 180, and if you subtract 90 from it, they have to add up to 90.
Yeah. If they all add up to 180, you've used 90 right there, then the other two have to add up to 90 as well. So let's look at this. So I've already pointed out that our book uses capital letters for angles. I'm not going to do it that way. A, B, and C are the sides. That's pretty universal. And these are two Greek letters. When we draw a triangle like that, I always want you to put a certain English letter across from a certain Greek letter. Okay? Just the way I have right here. What's the name of that Greek letter? Alpha. A across from alpha, always. How about the Greek letter across from B?
Beta.
Beta. Yep. Even if you draw your triangle this way, that's fine. You label the sides like that. Stick with C as the hypotenuse, though. Put A across from alpha, B across from beta. As long as you set up your triangle like that, that's just like a reflection of what I did, or a rotation, however you want to think about it. It's the same thing.
I thought it would be that way around.
So A always goes across from alpha, and B always goes across from beta. However you draw your triangle. I usually draw them this way. Okay, now let's find the sine of alpha. You can look at either picture, you'll get the same answer. What's the sine of alpha? A over C. Now, let's find the cosine of the angle that's complementary to alpha, beta. What's the cosine of beta? It's adjacent over hypotenuse, which is also A over C. Let's do one more of those. Let's find the tangent of one of the angles. What's the tangent of alpha? A over B. And now let's find the cotangent of beta. It's also A over B. So there's a special thing. I mean, I could keep going, but there's a special thing that's happening here. Okay? Sine, cosine. Tangent, cotangent. So there's a connection between the names there. We already know the connection between alpha and beta. They're complementary. So these are complementary. These functions are called cofunctions. And there are three pairs of cofunctions. Sine, cosine, secant, cosecant, tangent, cotangent. A cofunction is just when you take a trig function and you put the word co in front of it. That's all it is. Sine, cosine. Secant, cosecant. Tangent, cotangent. Now, the only one that matches up the way we're used to is tangent and cotangent. Tangent and cotangent have two special relationships. They're reciprocals, but they're also what we call cofunctions. So, the connection between these, they're cofunctions. The connection between these angles, complementary. And that gives us that theorem, the complementary angle theorem. It says that if you take cofunctions of angles that are complementary, the answers come out the same. So you look for two things, cofunctions and then angles that are complementary. So, just a quick example. What's the cofunction that matches up with sine? Cosine. What's the angle that's complementary to 15? 75. If you check that on your calculator, they will come out the same. doesn't tell you what it comes out to, but it does tell you that they would come out the same. Cofunctions, complements. Okay. So I'll show you how we're going to finish up and use that idea. I want to simplify that without a calculator. And on a problem like this, I'd probably ask you to explain how you get it. Sine, cosine. What's the relationship between them? Cofunctions. 35, 55. What kind of angles are those? They're complementary. So I'm subtracting cofunctions of complementary angles. So that means this and this, how do they compare? They're equal. I don't know what they are, but it doesn't matter what they are. I'm subtracting two things that are equal, so the answer would be 0. So the point is not to figure out what the individual things in the problem are. It's more to look at the big picture and realize, wait a minute, there's a pattern here. I don't even need to know what they are. I just get 0. What other operation would this trick work with? Division, addition, or multiplication? So if I change that to addition, what would be? Yeah, you wouldn't know the exact answer there. All you would know is you're adding two things that are the same. But if I say, what do you get when you add two things that are the same? Well, you get double the thing, but you need to know what the thing is. So it doesn't work with addition. It works with division. Tangent, cotangent, cofunctions. 20, 70, complementary. So what's the answer there? 1. Again, I have no idea what the tangent of 20 is. I'd need a calculator. I don't know the cotangent of 70, but I do know they're the same. So it's a little trick just to simplify problems like that. Any questions on that? All right. Okay, so homework, mostly in the book, 1 through 14, 16 to 20, 21 to 24. But I want you to simplify these last two problems, which, if you understand what I just did, they'll be very quick. That's the homework. Okay, so we'll take a look at that tomorrow, and then tomorrow we will finish up part 2 of that.